16.108 has a gear C that has a mass of 5 kilograms right here. Center point's B, part of the link of AB link right here. And it's got a centroidal radius of gyration of 75 millimeters. The uniform rod AB then has a mass of 3 kilograms and gear D is stationary. This is D out here. If the system is released from resting position shown, determine the angular acceleration of gear C and the acceleration of point B. I'm going to call the point in contact right here B prime that this gear C has with the outer gear D. We're going to set the mass of C equal to 5 kilograms, K is 75 Newton, or millimeters, excuse me. The mass AB is 3 kilograms, and R is 100 millimeters for the radius of this gear, and the cap L is 200 millimeters for the length of that rod. The acceleration of B can be written as the acceleration of B prime, this value over here, plus the acceleration of B with respect to B prime. The a sub B prime, since this is a stationary point out, there cannot be any acceleration in the J direction, so we can have some in the I direction. And then the acceleration of B with respect to B prime is going to be alpha crossed into a minus RJ right here, excuse me, RI. And there is no omega term because this is being released from rest, so there's no rotation. And so that means that this comes out to be, we can also set this A sub B, by the way, as equal to alpha crossed into the 200 millimeter or capital L times I. So it's alpha AB, K crossed I. So when you look at this, a K crossed I gives me a J term. This K crossed I gives me a J term, and it allows me to relate then that alpha AB is going to be equal to minus alpha R over L. All right. I believe it turns out from this situation, since there's no omega in this rod right here, that the only acceleration that B can have is vertical, and so this acceleration of B prime right here has nothing that can equal to on this side, so acceleration of B prime is going to be 0 as well. But we've got a relationship between the alphas right here. Let's look at the free body diagram on C, which is the disk, and we'll notice that you got MCG and you got a BX and BY there, you got a DX and DY out here at this point. And if we do the Newton's second law for it, we get the sum of the portion of y equal to m times a sub y. And so if you look at this, you're going to have a by plus dy right here minus m sub cg equal to m sub c, and then the alpha r is going to come from the alpha, it's going to come from alpha AB times L, but you can see that alpha AB times L is the same thing as minus alpha R, and so we plug that in right there. And then you take the moments about G for this thing right here and set that equal to I bar alpha, and the only force that's producing moment is dy, it's dy times R then equal to m sub c k bar squared times alpha. So that's going to be my equation 2 then. Now let's look at the free body diagram on the rod AB right here. You got an AX and AY out in the ends, you got a BX and BY right here that you relate to these, so in other words the BX got to be that way if it's this way on that one. If it's up on this one, it's got to be down on that one. And then you got your MAB times G. If you sum the moments about A, about a fixed point, you can set that equal to I sub A times alpha sub AB. And so what do you have for that? You'd have a minus MABG times L over 2 right here, and then a minus BY times L, and that's got to be equal to the I bar, or the I about the end of the rod is 1/3 ml squared, and then the alpha AB there is minus alpha over 2 from up there. So I'm going to call that equation 3. So in reality, what you got here is equations 1, 2, and 3 that you can solve simultaneously, and you get alpha then equal to 72.4 radians per second. And that's going to allow you to calculate A sub B out of this set of equations as well, and you get minus 7.24 meters per second squared J.